Welcome to The Explainer. Today, we are taking on the Cambridge 9618 Paper 4 exam. And specifically, we're translating all that abstract theory right into executable Python code. Because as you probably know if you're gearing up for this practical exam, it's really not just about knowing the theory. It's about flawlessly executing the syntax when the clock is ticking. So we're going to explore the predictive practice mark scheme together, translate that algorithmic logic into Python, and figure out exactly where those examiners are waiting to award or completely deduct your points. Let's get into it. Here is our roadmap for the day. We'll start with acing the paper 4 practical, then tackle question 1 on linked lists, question 2 on bubble sort, question 3 on binary trees, and finally, we'll wrap up with some final exam winning strategies. All right, section 1. Question 1, linked lists. Okay, look closely at the syntax for this node class. Notice those double underscores right before data and next node? That is absolutely crucial. The mark scheme is strictly looking for private attributes here. In Python, adding that double underscore triggers name mangling, which securely encapsulates the data so it literally cannot be accessed directly from outside the class. If we forget those underscores, we just lost the encapsulation marks. Boom, gone. Instead, we have to build getter and setter methods, like getData and setNextNode, to interact with those values safely. Now think about the exact sequence of events for the insertFront method. It's kind of like a delicate operation. Step 1, we instantiate a brand new node with our parameter data. Step 2 is where things get critical. We must link this new node's next node reference to the current head of the list. Why? Well, if you update the head pointer to our new node first, the entire rest of the list is permanently lost in memory. Poof! Only after the new node is safely holding on to the old front of the list can we safely proceed to step 3, which is updating the head to point to our newly minted node. Let's actually slow down for a second here. The delete method? Yeah, it's notorious for being the trickiest logic to nail down. First, we handle the edge cases, checking if the list is empty or if the head itself is the target. Then we use a current pointer to traverse the list, looping continuously while current.getNextNode is not none. But look closely at that final step. When we finally find the node right before the one we want to delete, we call current.setNextNode, and we pass in current.getNextNode.getNextNode. I know it's a total tongue twister. But in Python, this literally tells the current node to bypass the adjacent node entirely. It surgically removes it without breaking the chain. Moving right along to section 2, question 2, bubble sort and file handling. So we're dealing with raw CSV format from a file called studentdata.txt that we need to parse. As you can see, we've got a list of names and their corresponding scores. Our mission is to read this data in, sort it in descending order, and write out the results. Just as a little teaser looking at the raw data, Samuel Guattari is our top scorer with a perfect 100. Our code needs to successfully find him and elevate him to the very top of our sorted list. Right, so how do we actually get that text file into our Python arrays without everything breaking? This specific little snippet is going to be your best friend. Using withOpen is the examiner preferred way to handle files, simply because it acts as a context manager. It automatically and safely closes the file when you're done, even if a random error pops up. Then, for every single line, we use .strip.split. The strip method elegantly removes any of those pesky invisible newline characters, and split gracefully separates that comma-separated string into a neat Python list. This lets us easily pop the names and scores right into our parallel arrays. Okay, listen up, because this is literally one of the biggest gotchas of the entire exam. When you're writing your bubble sort algorithm to sort these scores in descending order, you're constantly swapping values around in the scores array, right? But remember, the names array is running in parallel. If you swap the scores array, say moving Samuel's 100 up to the top, you absolutely, positively must swap the parallel names array at the exact same time using the exact same indices. If you forget to do that, well, you'll end up assigning Samuel's perfect score to Alice Wanji, and the entire data set is completely ruined. All right, boss battle number 3. Section 3, question 3, binary trees. Now, interestingly enough, the encapsulation rules completely flip on their head here. Unlike the linked list we just built, the mark scheme for the binary search tree requires the book node attributes, things like ISBN, title, left node, and right node, to be entirely public. No double underscores to be found here. It's a really great reminder that different data structures demand different object-oriented setups. We really have to read that prompt carefully to figure out exactly what kind of access the examiners are asking for. Let's walk through the actual logic of the insert method for this tree. We always start by initializing a current pointer to the root. Then we enter a continuous loop, where we're essentially making a left or right decision at every single node. We look at the new book's ISBN and compare it to the current node's ISBN. If it's strictly less, we traverse down the left branch. If it's greater than or equal to, we traverse down the right branch. We simulate this exact path, stepping down the tree over and over until we finally hit a none value, an empty slot. And that is precisely where our new book node gets permanently inserted into the tree. Now, check out the exact sequence of the in-order recursive method. Honestly, this is where the magic of binary search trees really shines. First, we recursively dive all the way down the left branch. Then, and only then, do we print the current node's ISBN and title. Finally, we recursively dive down the right branch. Because of how we meticulously inserted the data earlier, smaller stuff to the left, larger to the right, this exact left, print, right sequence mathematically guarantees that the entire library catalog will print out in perfectly ascending ISBN order. It's pretty satisfying. Almost there, Section 4, Final Exam Winning Strategies. First things first, we absolutely have to talk about this quote straight from the exam instructions. A mark of 0 will be awarded if a programming language other than those listed here is used. The approved languages are Java, Python, and Visual Basic in console mode. Look, you could write the most perfectly optimized, elegant sorting algorithm the world has ever seen in C++ or JavaScript, but if it's not Python, Java, or VB, your result is a flat 0. So, sticking to the approved languages is step 1 for sure. All right, let's hit some rapid-fire mark-winning habits that come straight from the examiner notes. Minor syntax details really do capture major points here. In your bubble sort, always include a swap flag. If you complete a full pass with absolutely no swaps, break the loop early for efficiency. That is literally a free mark. In your linked list, never ever move the head pointer during traversal. Always use a secondary current variable. When you're writing to sortedresults.txt, wrap your file writing code in a Python try except block. The mark scheme explicitly rewards you for intercepting I/O errors rather than just letting the program crash and burn. And lastly, when you are asked for evidence, ensure your screenshots clearly show the exact outputs requested, like the literal words true or false for your search functions. As we wrap up this explainer, I really want you to think a little bigger, beyond just the exam room. Yes, memorizing this syntax and mastering these data structures will help you bag those 25 marks on a question. But the principles you just built from scratch, like the incredible O-log-n efficiency of traversing a binary search tree instead of blindly searching a flat file line by line, these are the exact foundational algorithms that allow real-world databases to search millions of records in mere milliseconds. So how might the efficiency of the algorithms you're writing today shape the massive software architectures you'll be building tomorrow? Keep experimenting with your code, and best of luck translating these concepts into reality.